So we're going to start with the first part, that is conformational analysis. So, okay, so there is a difference between these two compounds and these two compounds. We call these compounds as, these are configurations. Now, configurations are the different arrangements of atoms in the space, but I cannot change this form into the other form by simply rotating the bonds. Because if I'll rotate it, it won't change to the other form. It will remain in the same configuration. I can change this configuration into other configuration only when I can break these bonds. I will break this chlorine and allow it to attack on the other side. Iodine will leave and iodine will come on this side. So this completely involves bond breaking and formation process. You cannot convert one form to the other form simply by means of the rotation. But in the case of these two compounds, we call them as the conformations. In the case of conformations, we have to remember we can change one form to the other form simply by rotation around the carbon-carbon bond. This is carbon-carbon single bond. So this can be changed from one form to other form without affecting the bond strength. That is very important. So we call these structures as the conformations. Now, in the case of the stability of these two conformations, we have studied the energy profile diagrams. Now, in the case of energy profile diagram, I will draw it for these two. So let's say I'm drawing for the ethane. So on the y-axis, I will present the energy, and this is presenting the dihedral angle. Now, what is dihedral angle? Let's say I'm drawing for this Newman projection, this hydrogen, and this hydrogen. This is eclipsed form. That's why we have. Now the plane containing this hydrogen and the plane containing this hydrogen, they are in same plane. They coincide with each other. And that's why the angle between this plane is 0 degree. Similarly, if I'll draw it for this staggered form, this is the front carbon and this is the backside carbon. So the plane containing this hydrogen and the plane containing this hydrogen, the angle between them is 60 degree. Okay, so we call this particular conformation as a staggered conformation. So now what is happening in the energy profile diagram, I will start from 0 degree. So in the 0 degree conformation, these two hydrogen, they have their specific van der Waals radii, and they try to come more closer than their sum of their van der Waals radii. That is going to create the repulsion between them. And that's why at 0 degree, the energy level of this conformation will be very high because it's having more repulsion. But as it comes to this 60 degree, at 60 degree, these two hydrogens are away from each other. And that's why there is a less repulsion, more stability. And that's why we are expecting this kind of. So that's why we are expecting this kind of curve. Now this will reach again at 120. This will come again at 180. So like this. But in case of butane, sorry, in ethane, remember this 60 degree and this 180 degree, they are not different because we are finding or we are coming across the interaction between the hydrogen atoms only. So 60 degree and 180 degree will have the same energy levels because they're going to experience the same kind of repulsion. Okay. So now there is one word conformations and the other word is conformer. There is a difference between these two words, remember. Now, when I talk about the conformations, there are numerous number of conformations present in the compound. Because if you talk about 0 degree, 60, 120, there are various angles available. You can take 0.1 degree, 0.2 degree, there are also different conformations. So all these conformation, in the case of ethane, there are numerous number of conformations are available. But conformers are only those which are the minima of the energy profile diagram. I will only focus on this because this and this is same. So this minima of the energy profile diagram is called as conformer. So staggered is the conformer of the ethane. Okay, so how many conformer are there for the ethane? One. How many conformations are there? There are numerous conformations. All conformers are conformations, but all conformations are not necessarily to be conformer. Okay, now I will take one more example here, that is of butane. So in case of butane, we write the structure as CH3, CH2, CH2, CH3, and we just observe the Newman projection across these 2 and 3 bonds. So when I talk about it, I'm drawing the Newman projection. Okay, so these are all different conformations of the butane. Now you can see the dihedral angle between the first two methyl. We are going to focus on these two methyls. So here the dihedral angle is 0°. Here the angle is 60°. The next angle is 120°. Next angle is 180°. Next is 240 and 300. And finally at 360 we'll come to the first structure again. Now in the case of the nomenclature of these conformations, we'll be using two words. One is the periplanar word. The periplanar means the two groups are in same plane. And the second one is the clinal, where we say they are in different plane. Also, two more words. One is anti, when the two groups are on different sides. Or not different, I will call it as opposite side. Okay. And the second one is syn, where they are on same side. So using these words, we're going to define each and every conformation. So let us talk about conformation number 1. Two methyl groups are on same side. So I will call it a syn. And they lie in one plane because the dihedral angle is 0 here. So this is syn periplanar structure. The next one's second conformation, where still the two methyl groups are on same side, but they are not in same plane. So this is synclinal. Now this is kind of axial equatorial position. So the methyl groups are on opposite side. Axial is upwards, equatorial is downwards. So here they are anti, but they are anticlinal. Fourth one is the most important structure, where the two methyl groups are far away from each other. So this is anti, but this is periplanar because their two planes are coinciding. Then we have the fifth structure, which is also anticlinal. If you'll see the third and the fifth structure, they are going to experience the same kind of repulsion. And the last one, sixth, which is similar to the second structure, which is your synclinal structure. Okay, so when you draw the energy profile diagram for this, remember, in the case of energy profile diagram, this is presenting the dihedral angles 0°, 60, 120, 180, 240, 300, and finally we'll come across 360. So at 0°, this structure is going to experience more repulsion because the two methyl groups are very close to each other. So this is going to have the highest energy repulsion. At 60°, this energy will decrease, but it won't be much, like it is not a more stable structure. Still, there is some kind of repulsion is there. From first conformation, we have come across the second. Now we'll talk about the third conformation. Now in case of third conformation, again it is coming to the eclipse, but this eclipse and the first eclipse is different, because in the case of first eclipse, there is more repulsion between two methyl groups. In this case, there is a less repulsion. And that's why in this case, though the energy level is increasing, but it will not increase to this level. It is lesser than that. The fourth structure is the most stable form, and that's why the energy level will be very low, which will again change to the fifth structure, which will have the same energy level like your third. So this is fifth structure, is again anticlinal. Fourth is the most stable form, and then it will go to the again the energy level like second, and finally it will reach to the again 0 at 360. So how many minima are there over here? There are 3 minima in the case of butane, and that's why there are 3 conformers. How many conformations are there in the case of butane? There are numerous number, but how many conformers are there? 3. Out of this, which is the most stable conformer? That is anti-periplanar. Anti-periplanar unit is also called as the anti-butane unit. Remember this word, because this is we are going to use for the current syllabus. So this is anti-butane unit. Okay, so this kind of analysis, studying the relative stabilities of the compounds on the basis of internal forces and their properties, how they are affected due to their structures. These all studies, we call it as the conformational analysis. Now, while studying the conformational analysis, we are going to come across the various terms. So these terms, I will explain it to you. So this part, we are going to talk about types of strain. In the case of types of strain, the first strain that I will talk is the Baer strain. Baer strain is also called as the angle strain. Now, what is meaning of the angle strain? This is something, a comparative study of the carbon from its expected angle. For example, if I say the carbon is present in its respective carbon is present in its saturated ring form. So I have a carbon in the saturated ring form. So what is the angle here? The angle is 109.5 degree. But if I arrange the same carbon in the cyclic form, this is also saturated sp3 hybridized. But what is the angle here? 60 degree. So the angle is deviated from the normal expected angle. And because of this deviation, there is some strain in the ring. How to calculate that strain in the ring? For that, we have a formula. And the formula says the angle strain is equals to half into the reference angle. I will call it as a reference angle because here we have considered the carbon is at in the sp3 hybridization. We can have a different hybridization, and accordingly the angle we will select. Minus alpha. Alpha is the internal angle of this cyclic chain. So this is half into 109.5, which is the expected angle, but actual angle is 60. So this comes out to be around 24.75 degree. But if I calculate this for cyclobutane ring, over here the angle is 90. So what happens to the angle strain? Half into 109.5 minus 90 degree. So when you'll calculate for this, the angle comes out to be around 9.75 degree. So if you'll see, from propane to butane, the angle strain has decreased because as you go on increasing the carbon atom, this carbon-carbon-carbon chain goes on opening up. So they are free to have the more angle towards the 109.5. And that's why angle strain goes on decreasing. Okay, so angle strain is something a deviation from the expected angle which creates the strain in the molecule that we calculate using this formula. Second type of strain that I'm going to talk is the van der Waals strain, or which is also called as the steric strain. For this, I will take the same example of the ethane present in the eclipse and the staggered form. Now, over here, the repulsion is more in the case of eclipse form, and here it is the less. So when these atoms crosses their van der Waals radii, they start repelling each other, which creates the strain in the molecule. That strain, we call it as the van der Waals strain, or we call it as steric strain. This is existing between the atoms attached to the adjacent carbon. These hydrogens are not directly attached to each other. They're attached on the adjacent carbon and they're creating the strain. The third type of strain that we will discuss is the torsional strain, or we also call it the Pitzer strain. Now, what is this torsional or the Pitzer strain? Now, when I talk about this eclipsed and the staggered form, if I say they're free, they're allowed to rotate freely in the compound, then what will happen? There will be random rotations and there will be more disorderness in the molecule. This disorderness definitely is going to give us the higher entropy. Entropy is disorderness in the structure. So if these molecules are allowed to rotate freely, they will create more randomness, more disorderness, and that's why there will be more entropy. But actual entropy is found to be less than that. That means they are not free to rotate. And since they are not free to rotate, there is some energy barrier. If you'll see, this energy barrier in the case of ethane is around 3.3 kilocalories per mole. So that difference they have to overcome to change from one form to the other form. And that's why these molecules are expected not to have a random rotation, because of there is a strain in the molecule that's called as a torsional strain, that energy difference. Okay. And the last type of strain that we will talk is nothing but transannular strain. Now, in case of transannular strain, I will take example of simple cyclohexane. Now, cyclohexane, we know it's present in the six member. This is planar form, which is not actual form of the cyclohexane. It's stable in its chair form. But there is one more conformation for this, which is possible, is the boat form. There are various conformations, but I'm taking this boat form specifically because if you'll remember, in the boat form, these flagpole atoms, they come closer. Now, if you look at these two hydrogens, they are not attached to the same carbon. They're not attached to the adjacent carbon. They're actually across the rings. They're the atoms attached to the across the ring. But because of this non-planar structure, since these two carbon atoms come closer, this hydrogen crosses their van der Waals radii. And that is going to create the strain in the molecule. And that strain, we call it as the transannular strain. Okay, so these are the four types of strain: Bayer strain, steric strain, torsional strain, and transannular strain. So now the structures of in case of the cyclooctane, for that I will share chem sketch with you. Okay, so first we will talk about the structure of the cyclooctane. So when I talk about cyclooctane, these are the 8 carbon arranged in the cyclic form. We cannot arrange them in the planar form like this. So the most preferred conformation for this is the crown form. So in the crown form, the 4 hydrogen which I have highlighted here, sorry, carbon which I have highlighted here, this one, the alternate carbon, they are above the plane, and remaining 4 are the below the plane. If you look at the structure from the top, it may look like this, but remember, 4 carbons are above the plane and 4 carbons are below the plane. So it looks symmetrical like this. So previously it was expected that this structure is present in this symmetrical form in the highest population. But later on, through the NMR spectroscopy, even through the X-ray crystallography, and some free energy level calculations, it has been seen that it is found to be present in this boat chair form. Now, this is kind of like a boat, and this is kind of like a chair conformation of the cyclohexane type. So, this is having the boat chair conformation. Now, in this boat chair conformation, we'll see the first carbon having two hydrogens here. Now, this hydrogen will be involved or in the closer distance with the hydrogen atoms of the fourth and the sixth carbon atom. So, they will have a kind of a repulsion between them. This strain we have already discussed is called as the transannular strain. So, there is a transannular strain between the hydrogen atom of the first, fourth, and the sixth carbon. Similar kind of the interaction is also expected between the proton of fifth carbon, seventh carbon, and the third carbon. They will also have the transannular interaction between them. So, this transannular interaction is exhibiting between the hydrogen atoms of the first, four, and six carbon, as well as of the third, fifth, and the seventh carbon. The hydrogen atoms which are involved in this kind of strain are called as the intra-annular hydrogens, while the one which is present here, which is not involved in any kind of interaction, we call it as the peripheral hydrogen. So in the cyclooctane, the six are the intra-annular hydrogens and the remaining are the peripheral hydrogens. This kind of strain can be decreased by means of changing the hybridization of the carbon. We can change it from sp3 to sp2 hybridization. So we can replace it by the carbonyl group, let's say. So if you replace it by carbonyl group, this hydrogen won't be there to involve in the transannular interaction. So obviously the strain will be reduced in the molecule. You can also replace these carbon atoms by some heteroatoms like oxygen, sulfur, or nitrogen. So that will also reduce this transannular strain. Now we will discuss the structure of the cyclodecane. Now cyclodecane also exists in the different conformation form, but the most populated one, I have drawn a structure here. This is kind of like a boat. In between there is a chair form, and again this is an inverted boat. So we call this as boat chair boat conformation. Now in this boat chair boat conformation, let us concentrate on carbon number 1. Now this carbon has two hydrogen. One is here and one is here. Now the one on this side will be involved in the transannular interaction with the carbon number 4 and carbon number 8. Okay, so there is a transannular interaction between the hydrogens attached to the carbon number 1, carbon number 4, and carbon number 8. Okay, so at first carbon we can see one is the intraannular hydrogen and other is the peripheral hydrogen. Similarly, over here, the hydrogen atom attached to the third, sixth, and the ninth carbon. They are also involved in the transannular interaction. Okay, so now we will concentrate on this few carbons specifically. If you look at this structure, if you look at this first carbon and third carbon, let us compare them now. In the case of, just I'll draw the normal bond here, hydrogen. Now if you'll see here, in this case, this is an axial bond and this is an equatorial bond. So at the first carbon, the axial bond is intraannular and the equatorial bond is the peripheral.
Whereas at the third carbon atom, the axial is a peripheral and equatorial is a intraannular. So the first carbon and third carbon, they are not same. They are having different environments. As well as look at this second carbon. At this case, in this particular case, the two hydrogen are not involved in any kind of strain. Both are peripheral, axial as well as equatorial. So there are three types of carbon. These 10 carbons overall in the structure are divided into three types. Now, what are the three types? The first type, in which the axial proton is intraannular and equatorial proton is peripheral. Second type, where both axial equatorial are peripheral. Third type, where the equatorial is a intraannular and the axial proton is the peripheral. So out of 14 hydrogen, total there are 14 hydrogen in the structure. So out of this 14 hydrogen, 6 hydrogens are intraannular, while remaining 8 hydrogens are peripheral. 10 carbons are divided into three types. Okay, the proper model of this structure, if you look compare it, it will resemble with the diamond lattice, because diamond is also made up of the cyclohexane rings in the chair conformation. So somewhere it is resembling with this cyclodecane structure. Now, in this case of cyclodecane, this kind of strain can be avoided or it can be reduced. As I have discussed in this case of cyclooctane, we can replace this carbon, we can with the heteroatom like oxygen, hydrogen, sorry, oxygen, nitrogen or sulfur, or we can just change the hybridization from sp3 to sp2 to reduce this strain. Now, there's a concept called as the ring flipping or the pseudo rotation. We can avoid that pseudo rotation. Ring, see, if I'll compare it with the normal cyclohexane ring, that undergoes the flipping process very easily. But in this case, if I have to reduce the flipping process, what simply you will do is you will replace these hydrogens by some substituents. Especially this kind of geminal substitutions will be comfortable, because when you'll have this methyl groups over here, this compound will try to achieve its stable position where there is a no steric crowding because of this methyl group. And in that conformation, this compound will remain in the rigid form. It will not flip to the other form, because as it will change to the other form, these methyl groups can come closer and they can create the steric effect. That's why they will try to achieve only one conformation where the methyl groups are far away from each other, and that's the most stable. So in that stage, it will not undergo any flipping or the pseudo rotation process. Okay, so this is about the structure of the cyclodecane, and previously we revised about the cyclooctane. I have discussed only structural part of the cyclooctane and decane. In the next lecture, we will talk about the unusual properties that the medium size rings have compared to the small size rings and the larger rings. Okay, thank you.